It's time to learn about chemical equilibrium. This is screencast 14.1. What you'll learn is what it is in this particular screencast. And thinking deeper, you might come up with ideas when it does not apply, when chemical equilibrium has been destroyed. We'll see how people measure it. It's a rather unusual system. And we'll think about what these measurements mean. This value, KEQ, what does it mean if it's very high or very low? We'll name a couple of things about measuring this constant that are easy to forget, specific things about it that people oftentimes mess up. And finally, what does this woman running on a treadmill have to do with chemical equilibrium? Are you ready? Okay, let's get started. An introduction to chemical equilibrium. This is a state where chemical reactions are reversible. So if A and B are mixed together in some ratio, it doesn't have to be 1-to-1. The stoichiometry will predict that. It'll turn into some amounts of C and D, for example. It might just turn into C if it's just a synthesis reaction. But chemical reactions taking place, and something to consider is if two things can come together to react, why can't the products do the exact same thing and turn back into starting material? Are reactions reversible? The bitter truth is that they oftentimes are, and for a synthetic organic chemist, it's usually considered a hassle. You go ahead and make your product, you're so happy, and then you watch it turn back into starting materials. Well, who wants that? Anyhow, it's a state of reversibility, and a chemical equilibrium occurs not when the reaction is over, common test question, but rather when the forward rate is equal to the reverse rate. That's why we got this woman running on this treadmill. She's running, but she's not going anywhere. Her forward rate better be exactly equal to the rate that the treadmill is going in the opposite direction. Otherwise, she's going to smash into the front of that treadmill if she's going faster than the treadmill itself. Or she'll have that embarrassing situation that's happened to me and it's probably happened to a few of you where you fall or slip and you go winging off the back of the treadmill because your forward rate is not as fast as the reverse rate. Anyhow, they measure it using something called the equilibrium constant, and it's a measure of the concentration of C and D. You'll notice that's products, so the concentration of the products over the concentration of the reactants. Several silly things, or, well, niggly little things you don't want to forget about this. Number one, those square brackets mean concentrations in moles per liter. These C's and D's, the little ones, become exponents. So the coefficients become exponents, meaning they play a very large role in this reaction. Not quite sure why they did this. I'm sure they had their reasons, but it's something you just have to remember. And if it's less than 1, that's got to mean that the equilibrium constant means that mostly reactants. That means that, if you will, she's not running as fast as the treadmill is going. She can't keep up. And so you have mostly reactants. If it's greater than 1, she's perhaps going a little faster than the treadmill is going, and she'd be bumping into the front of it. And for a synthetic organic chemist or a synthetic chemist in general, somebody who makes stuff, that's usually good. In your body, there's probably good reasons for having something maintain that equilibrium where you need a little bit of that reactant. Usually, you just want that reaction to go forward. A very important thing about this constant is that it only works for gases. We omit, and aqueous systems. We omit liquids and solids. If you see an L in parentheses or an S in parentheses, we consider that to have left the reaction medium. Therefore, the equilibrium no longer exists. Left the equilibrium, left the mixture. It's gone. I hope that provides you some kind of a hint as to how we can make that equilibrium disappear or be destroyed.